right. Hello, ladies and gentlemen. It's meteorologist Jeremy Wheeler, and I'm here for WAVY Science Lab. Today, we're going to be talking about magnets and magnetism. It's the magic of magnetism. So hopefully we do you right and you learn something. And maybe if I could do some magic too, that would be pretty cool. I wouldn't mind that, but that might be a little difficult since I'm just a scientist. I've tried magic. I'm not very good at it. It takes a lot of skill, more skill than I realized when I tried, just playing around with it. Anyway, magic of magnetism today. And we're going to have some fun and learn a few things. We're even going to play with a few toys, AKA high-tech equipment, and might even do a few experiments. All right, so having said that, let's get to it and talk about magnetism. And so magnets, they're in our daily lives. Believe it or not, they're in a lot of things, a lot of electronics these days. So we actually don't really appreciate them that much. So let's talk about the history of attraction. So in the 1960s, you had Fred and Wilma Flintstone, and then in the 90s, 2000s, it was Friends and Ross and Rachel together, and then currently there's Travis Kelce and Taylor. Wait a minute. This is the history of attraction. We need to talk about the history of magnetism. Okay, so I got a little off track there. So let's talk about the history of magnetism instead. And so that's, I think, a little more apropos. And 600 BCE, before the Common Era, Greek philosopher Thales of Miletus describes attractive forces from lodestones. What is a lodestone? Well, a lodestone is a large mass of metal in the ground. You may have heard of the Mother Lode. There's a movie, Charlton Heston, I think 1970s or 80s. You hit the Mother Lode, and we talk about that sometimes when it comes to gold. A lot of times. This is one that has magnetic properties though. So that's what a lodestone is. And some of the old video games too, newer video games too, they might talk about lodestones and things like that. So anyway, that was 600 BCE, 460 to 270 BCE. The Greeks tried to use magnets for healing, and people still try and do that today as well. And the jury's still out, but some folks swear by it. Some folks say, it hadn't helped me at all. But there might be a little something to it. I mean, it does, our body's chemistry. Anyway, that was a long time ago that they tried it. Wet compass, known in China since ancient times. You can take a needle, maybe they got a needle from a lodestone or maybe some magnetic thing, and they rub it on either silk or wool or maybe even their hair, put it on a leaf, and then set it in the water, and it will right itself and point towards north. And so, the wet compass. But a dry compass, 2nd century BCE, a spoon was made out of magnetite and put on, some kind of rotating device. And so it was the first dry magnet. So the history of magnetism, the 1269 Petrus Peregrinus de Mericourt, hopefully I pronounced that right. I try and pride myself on that, but I try. Invented magnetic needle on a dry pin in a dry setting. Epistola de Magnete, I believe is that one. So that was in the 1200s. And then 1730, Survington Savory. Where do these names come from? Bound steel needles together and created a compound magnet. A permanent magnet was born. And then 1825, Francois Arago developed the first electromagnet. We'll talk all about that coming up in this session. So how do magnets work? All right, so you got these spinning electrons around a nucleus, right, in a magnetic field. It creates a magnetic field. Then we're talking about, I'm holding it. I'm holding billions, trillions, quadrillions of, atoms in my hand, air atoms, elements. So these electrons spin around a nucleus, and they create that magnetic field in a very small area. So the thing is, they're random. The directions are random, and so it negates each other. The forces negate each other, and they cancel each other out in a general substance. But in a magnetic substance, the electrons spin in the same direction. So now we got something going, and it creates that magnetic force. So electrons want to go from the north magnetic pole to a south magnetic pole. They want to go from north to south, basically. And so this creates that magnetic field, and it may cause some traffic jams in the universe. Anyway, so here's a picture of it. And so you can see there's a north and south NS. Anytime you see that from now on, north and south, North Pole, South Pole. So you can see the forces want to go away from that end and then around. And sometimes it goes straight out in a way, and we're going to talk about repelling forces as well. But the bottom line is that that they want to go from north to south, from pole to pole. And then if you have two of the same north and a north, they repel, right? And so these are two magnets, and the two ends trying to push them together, and it's sometimes you can force it together if you're strong enough. I've got a little example here. Let's see if I can do that. Yeah, that is. There we go. Yeah. So, I mean, I'm pretty strong. This is not the strongest magnet. And we're going to take a look at some of those magnets, some of those in just a little bit. But anyway, so the magnets, now you have different types of magnets. You've got the permanent magnets, magnetized ferromagnetic, iron magnetic materials retain its magnetism permanently. So there's a lot of magnets like that out there right now. I mean, there's billions of them, most likely, if not trillions. So neodymium, pardon me, and ferrite are two of the materials and that they use. And we're going to talk about that more too. So electromagnets, electricity creates an electric field, and these are often used in industry. So Earth's magnetic field, and we're not going to get too deep into this just yet, but well, we got a little time. So Earth's magnetic field, the Earth's outer core has currents of liquid, iron, and nickel. We talked about this in the moon podcast, the different cores. And so also in the sun, core has, so the Earth's outer core has currents of liquid and iron, and I believe the inner core is solid. And so these create electrical currents. So these electrical currents then, therefore, ergo, create magnetic fields in the Earth. And so the poles are created on the Earth. You got north and south. So we've got, that's pretty simple, but it gets a little complicated in here too. So here's some of those currents, around that core of the Earth, and you can see, where the mantle is, the cores, inner core, outer core. So you get these conduction zones, these fluid zones, and that's where they're created. So then you got the north and south pole. So the magnetic north and south poles are where the lines of magnetic fields converge. The geographic north and south poles are where lines of longitude converge, come together, right? But the thing is, those points aren't the same. Magnetic north pole is located near Ellesmere Island, Canada, about 310 miles away from the actual North Pole. And then compass points to the north, magnetic north. All right, we're going to take a break here on that note, and we're going to come back in just a little bit with more information. Stand by. All right, we are back, and today we're talking about the magic of magnetism. And we've got some magnets there. You can see some over on the side. I've got some demonstrations coming up here in a little bit. But we just got done talking about the Earth and Earth's magnetic field. So just kind of recapping that, we've got the magnetic north and south poles are different from the geographic north and south poles. And so there is a difference. There's a declination. So they've actually made a model of this, a world magnetic model produced by the United States National Geospatial Intelligence Agency and the UK's Defense Geographic Center. And I think that's how they spelled defense with a C. But anyway, updated every 5 years, and they, because these change, the magnetic North Pole is moving, believe it or not, and so it is moving. Elements in Earth's crust also can have an effect, so keep that in mind when you look at this map. And so we've got the map here, and you can see kind of the South Pole is very obvious to me. The North Pole actually isn't that obvious, but that's because of the way the map is laid out. But again, up there around Ellesmere Island in Canada is where geomagnetic north is. And so it's moving. It moves throughout time. It's not a solid point in the Earth. It's not tacked down, so it does move. And I believe it picked up some speed for a while, slowed down. But the bottom line is, they are tracking that, and it's pretty neat that it changes. The Earth is spinning and it's moving, and so, but there's also wobbling in there a little bit, things like that, and all these elements probably moving around too. So they are worried. Not worried, but concerned a little bit about at some point a geomagnetic flip. And that could happen at some point, a geomagnetic flip where the North and South Pole change. Now, I've read some articles, and some scientists say that, it would take thousands of years. Some say it would be less than that. most agree that it wouldn't be instantaneous, but it would have a big effect, because if you think about that, and let me go back to this graphic right here. So the thing is, if you flipped the north and south, let's say instantaneously, there's a low chance of that, then all the geostationary orbiting satellites in space, all the magnetic things, a lot of electronics things that we use would have big disruptions, because now all of a sudden everything's flipped. Mapping, for instance, would be a big problem. So again, most likely it would take 1,000 years for a magnetic flip to happen, but it could happen. So it could happen. Okay, so let's go back to that thought, and there's a magnetosphere, which is very important. That protects us, protects our daily lives. It's a giant bubble of magnetism in space, protects the Earth from harmful cosmic rays, especially from the sun. But so the solar wind puts out these high energy particles, right? And it's coming, 1,000,000 miles per hour or more towards the Earth. And if we didn't have the magnetosphere, it would probably strip away our atmosphere. Maybe not right away, but over time. I don't know exactly about the details about that, but it would strip away our atmosphere. And so that would not be good. We would not be able to breathe. Causes a bow shock in a weird shape. So because, right, it'd be radial, the force is radial, but then you've got this force coming in from the sun. So this is from NASA, JPL, Jet Propulsion Lab, and so you can see the Earth there, and putting out that magnetic field, the magnetosphere. But then the bow shock is where that 1,000,000-mile-an-hour wind is hitting that magnetosphere, and there's a shock, like a shock wave, from breaking the sound barrier. I believe I think it's something similar to that, but not exactly. So anyway, you got the solar wind coming in and causing that. Pretty cool to see. I mean, this, you can't see that if you're in space, but it can get mapped out, I believe, but you couldn't actually see this, but it's so cool, the representation of it. I've seen that even when I was a kid. I thought, that's so cool. I want to go up in space and see that. Well, not exactly. So, and then you can have coronal mass ejections, which we've had recently even, and, it can be strong enough that that's a mass that comes off the corona of the sun and then heads towards the Earth, and that can cause disruptions as well. So the coronal mass ejection, the sun's corona, the outer part, shoots out a mass of plasma and magnetism, and then that travels not as fast, I don't think, as the solar wind, but I mean, still, very quickly, and can be here in a matter as little as 15 to 18 hours or several days. So this is from NOAA. This is from National Oceanic Atmospheric Administration that put this out, and so it's interesting that there's that much of a difference. But I guess it takes the amount of energy and things like that. So this is bad. The coronal mass ejections, if they're big enough, it can try and chip away at that magnetosphere, but it can really disrupt the Earth's magnetic field, and the problems with spacecraft, satellite, power distribution, things like that. And we have this happen. I mean, it has happened, and it could happen again easily. So this is a picture of that, and so it's what we're looking at is the sun is covered up by a disk because it's so bright, but you can see around that disk. So that's what that circle in the middle is. You got the white circle. Well, there's a kind of a reddish circle outside of that. And then you got the different ways to view it. So you can see that mass come off of the corona and just, spew out away from the sun towards the Earth, sometimes towards the Earth. It's random, but it can move towards the Earth and disrupt things, and you can get the aurora borealis to form too. But that magnetosphere is getting disrupted by this coronal mass ejection. So it can cause big problems if you get a big enough one. You can have power lines, I believe, even take a hit, and they can be affected by electromagnetism. And this is a lot of electronics have this. If it was strong enough, it would affect electronics day to day. But this is a magnet from a hard drive, believe it or not. So that's pretty cool. There it is. That's an actual one. You can see it there, given to me by one of the engineers. They didn't need it. He said he didn't need it. But yeah, I mean, if it was strong enough that even these could be affected directly, but most of them are affected indirectly through the satellites and things in space, and then the connections. But we could, if we had really bad one of these, then yeah, it could. And then solar flare also would be also really bad. There's a really bad solar flare. So coming directly from the sun. So this is these are geomagnetic storms, CMEs. We talked about the Earth a lot, but now we're going to start talking about some more fun stuff, which that's pretty cool stuff. But we're going to talk about some fun stuff. We're going to have some time for some experiments here, and I've got I've purchased a whole bunch of things, and I showed you some of them. There's some little magnets you can get off the internet, and these are bar magnets as a horseshoe magnet. And so what we're going to do is we're going to take a look at what happens when some of these interact with each other. One just did because it just connected, even though I set it over there. So that's coming up in just a moment, so stay with us. All right, we're back, and we're talking about magnets, the magic of magnetism. And we got one thing over there, a toy that I kind of set up and just made a weird, I don't know, structure. I don't know, but yeah, it's just a cheap set of toys. And then there's another one over here that I've got as well. And so we'll take a look at some of that. But I've got some actual technical equipment here, and safety is key, right? We always practice safety. So yeah, I got all the full gear out just to make sure that we're safe with these giant cars, these huge, big well, maybe they're not that big. They're actually quite small, and that's one of those grabbers, those metal grabbers. Anyway, there it is. So we've got the two little vehicles there, and they're connecting to each other, and so you know, it's that simple. You basically have. Let me reload it again. You've got the North Pole, the South Pole colorized by blue and red. And so opposites attract. So as they get closer, then they have that attraction, and voila, there you go. So then what would happen if we were to reverse those mini vehicles and try and connect them? Well, let's find out. So we'll use our very safe equipment glove there, and try and see if we have the north versus north, or south versus south. I think I forget which color. Oh, it's trying to turn around. Remember, if you do it exactly, well, not exactly, but you know, you got the points there pushing outward away from each other. Then you know it's easy. But sometimes you get it off just a little bit, it starts to attract, and so that's what happens in that case. Let me load it again. So we got the two vehicles, again, north and north. And so, again, maybe I overdid it on the safety on these things just a little bit, but I just, hey, we practice safety. You never know, these things could fly up and hit me in the eye or something. So, of course, I did that in my garage. But so the actual cars are right here, and I don't have my safety equipment. I don't think I need them, but yeah, there it is. So you see the blue and reds kind of meeting. Very cool. And these are pretty cheap. You can get these off the internet and play around with them. They've got toys. They've got science experiments, all kinds of stuff like that. All right, so let's move on to the next experiment. And so we've got the bar magnet here, or the horseshoe magnet, pardon me. And one side is north, one side is south, polarized. And so these are iron filings. And I used to, when I was a kid, you know, in science class, I was like, well, aren't they fillings? I mean, it's not filings, but no, you know, if you were to file off some iron off of something, and then you would get that. And so you can see, you know, it attracts on both sides. They don't repel, but yeah, that's really cool. And they've got those toys that you can get. They used to have them where you had the face on just a piece of paper, and then you had the plastic, and you could actually move the thing around and make like a beard on the person. You could put a mustache, beard, change the hair, the face, and things like that. Very cool. That was years ago. I think they still have it, but I don't know. I haven't seen that in a long time. But yeah, very fun to play around with that. And the iron filings are right here. And I mean, as you can see, you know, they're on the bottom, and then you can just get the magnet and get it going there and play around with it. And so we can do. I could do this all day, right? Captain America. I could do this all day. But yeah. So there's the iron filings. Now there's one more experiment here, and so this one is a magnet. And so we've got a little itty bitty magnet here, and it's got north and south polarization. And so there's a bar magnet. And so when you put it in there, there you go, it attracts. So, you know, it would attract just to magnetic north in you know, the Earth, but this is more dominant because it's closer, right? It's proximity. So it takes over. And so, and I flipped it around enough you saw, but the magnet also flipped there. So that's pretty neat to see. So the, you know, maybe, is it red and blue opposites? Let's get it in there. Let's find out. Come on, let's place your bets, place your bets. So, okay, so blue and white, I guess, are opposite then in this case. And then when you flip it around, yeah, well, hey, well, there you go. Red's trying to attract a red. Pretty neat. So anyway, so yeah, and then this can disrupt some of your electronics too. I mean, this is a magnetic compass, but that can happen. Even if you have, I used to have a speaker, they have magnets in them. So electromagnets, usually a coil of wire wrapped around an iron rod. And when electrical current passes through the coils, a magnetic field is produced. When electricity stops, then the magnetism stops. And I admit, I made one in the garage, wrapped a copper coil around a nail, and it didn't work. And I tried a couple different batteries, things like that. You got to play it safe. I used the internet instructions, but it didn't work. So I didn't show it. I didn't bring it in. So it feels a failed experiment. But I've got examples of one. Whoa, yeah, take a look at this crane. Kids, yeah, that's cool. Very cool. So there's a magnetic crane right there, and a couple of them. And so the junk yards, the scrap yards will use them. And you know, you've seen in the movies, they'll pick up the cars and put it in the cruncher, and this is just a bunch of scrap. But very cool to see that, and a lot of magnetism in that involved. You know, if you were to hold on to something, it would probably pick you up, depending on what kind of metal you had. So it'd probably pick you up all the way. It's that strong. All right, so magnets and electronics, mainly neodymium, I think is how you say that. Made of neodymium, iron, and boron, developed in the 1980s. Gotta work on that. Highly magnetic, compact, durable, and corrosive, anti-corrosive. So electric motors, hard drives, speakers, medical devices, rare earth mineral. That's very increased demand lately because a lot of things use that. All right, so we're going to finish it off then. Environmental tip of the day, e-cycling. Old computers, phones, TVs, they have hazardous materials. They got magnets in them, but they got hazardous materials in them too. So you want to try and e-cycle them if you can. Find a reputable place near you that doesn't ship overseas. They're doing less and less of that now. You may make a little money off it too, but you know, the thing is, what they used to do is they used to ship it all overseas, and then it's hazardous because those little particles eventually, you know, you're taking them apart and crashing, and so people would breathe that in. So that's not good. But anyway, you know, e-cycling is a great way to try and alleviate that, and there's less in the dumps. All right, so I hope you learned a little something about magnetism today. Very cool. We had some fun with experiments. I'm meteorologist Jeremy Wheeler with WAVY Science Lab. Have a good day.